Good afternoon from Australia. Hope you're all doing well. I'd like to thank the organisers for giving me the opportunity to speak about my work and share it with you. This particular image has actually not very much to do with searching for high redshift radio galaxies, but when I saw that the Helix Nebula was on the poster for this conference, I suddenly realised that I'd serendipitously found it in a deep low frequency radio survey that I've been working on, and this just demonstrates the ability of these deep surveys to pick out these faint things. So if anybody's interested in planetary nebulae, please get in touch. There we go. So I'll just very briefly give some motivation as to why I'm doing this. I imagine most people are very familiar with this, but why are we looking for these black holes in the early universe? Well, I think one of the most profound results in current astronomy is the M-sigma relation, the correlation of the mass between the black hole and the bulge mass of the galaxy. But how was this established? Because this clearly links the growth of structure on very different scales. And furthermore, we're beginning to find all these very large black holes in the early universe. So these have been found from QSO surveys up to redshift greater than 7. And this implies the existence of very large seeds or incredibly fast growth. But then JWST is changing this field very, very rapidly. There are papers almost every day on the archive about new discoveries at high redshift. I just highlight a couple here. On the bottom right is a discovery of a supermassive black hole at redshift 8.7 with a mass of about 10 million solar masses. So I believe at present this is the most distant supermassive black hole we know about. So it's very exciting that it's so large, and it helps constrain the models on how these things are produced. In the top right is another recent result from Hurricane et al., finding lots of galaxies at redshift 4 to 7, which seem to have black holes which are far too massive compared to their host galaxies, particularly when you compare it to the local M-sigma relation, which is indicated by the grey shaded line. All these JWST detected galaxies are well above it. So this seems to be telling us something about how the black holes formed and how they're related to the growth of their host galaxies. And briefly, why are we looking in the radio? Well, most AGN are obscured, and this is particularly true at high redshift. So if the radio production is independent of how or why they're obscured, then we can perhaps find a representative sample. Nowhere near complete, of course, but it will be representative. Furthermore, the radio jets impact the environment via inverse Compton, as well as drilling into the dense universe at the very early times. And potentially this could be a unique probe of the EOR via absorption of the redshifted 21 centimeter line in low radio frequency observations. This plot on the right is just a simulation, of course, of what the SK might be able to do in the future. So briefly, I'll talk about the progress to date, finding powerful radio galaxies in the distant universe. So this plot shows the situation around 2018 for 500 megahertz luminosities as a function of redshift. Below redshift 6, I'm only really considering very powerful radio galaxies and obscured galaxies, so not the many radio loud QSOs, which would fall in the bottom left down here. I just don't plot them for clarity. So the record holder for powerful radio galaxies is this object here, discovered in 1999, TNJ 0924, and then this other object close to it, discovered by Matt Jarvis in 2009. Then these two QSO above redshift 6. This top object is probably a blazar, so its radio emission is beamed. But you can see we're finding there's no powerful radio galaxies at higher redshift. Then there was a flurry of activity over the last few years with one galaxy, redshift 5.7 from TGSS, then a whole bunch more from the same authors over a wider redshift range. Then one of the radio galaxies that we discovered at redshift 5.55, slightly more radioluminous, but still not breaking the redshift 6 record. Then there's a whole bunch of new QSOs detected in the radio, partly courtesy to the new radio surveys being conducted in the southern hemisphere. But these, of course, are a lot more luminous. I'm not sure what the change there was. Oh, yes, sorry, you might not be able to see it, but down here is the COS 87259 source detected at redshift 6.9, which is the most distant radio detected galaxy that we know about, but found from the deep survey in the Cosmos field, and it's only very weakly radio loud. Just a few weeks ago, there was this source here at redshift 7.6 reported on the archive, but it's only a photometric redshift, so this is yet to be really confirmed. So that's where we are, but we still want to find the powerful sources at higher redshift, above redshift 6, should they exist. And here's another recent result from Gludemans et al. Earlier this year from low-far surveys, but these are all far less luminous than the kind of sources we're looking for. So how do we find these needles in this sort of multi-wavelength haystack? So from the KZ relation for powerful radio galaxies, we know we have to go deeper, because galaxies at the highest redshift will of course be faint because due to cosmological dimming. That goes without saying. On top of all these optical near-infrared surveys that are about or coming online soon, we've got all these radio surveys coming along. So Matt already mentioned the MIGHTY survey from Meerkat, but there's even wider surveys in terms of coverage from both MWA and ASCAP, both based in Australia, and SKA precursors. So how are we planning to do this? So what's been our strategy over the last few years? Well, because we expect our radio sources to be compact, we expect that their spectral energy distributions at low frequency will be turning over, as shown in this plot on the left. So at low frequencies, this turnover can be measured over the frequency range covered. And it also means that our sources don't get fainter due to the effective negative K correction. We believe that our objects are compact because they're young, and also because the universe is very dense and it's very hard for the radio galaxies to grow to large scales. And of course, we expect them to be faint in K-band, as demonstrated by this image on the right, with no detection of a host galaxy down to K-band of 24. So this was the pilot from a few years ago. I already mentioned this first source, 0856 in the middle, which was discovered through ALMA spectra. You can see two bright ALMA lines confirming a redshift at redshift 5.55, almost exactly a billion years after the Big Bang. This other object on the left, on the right, 0917, was much harder. It didn't have any features in the ALMA spectra, so we had to take other means to get its redshift. And we ended up getting a Hubble GRISM spectrum shown below, and we had a strong detection of the O2 line, plus some weaker detections of other features which, while it's not very clear in this spectra, are very clear in the 2D spectra. So this confirms the stellar mass of this galaxy by getting the redshift. So now we're moving on to the full sample following the success of our pilot. So we refined our selection technique a little bit, learning from our pilot, but now we looked over the full area of Viking, and then we followed up good candidates with deeper Hawkeye data, plus, thanks to Helmut, the great Sharks data. And our results are shown in this plot here, showing the 150 megahertz flux plotted as a function of K-band flux density. And you can see that our candidate sources in black and red all have very extreme radio to infrared flux ratios, 10 to the 4 to 10 to the 6. They're comparable with known radio galaxies at redshift 3 to 5, the blue crosses, as well as the handful of radio galaxies known above redshift 5 over here. And very excitingly, we get these non-detections at the faintest K-band fluxes, which are superb candidates for potentially being at the highest redshift. So we got ALMA data and more spectral scans to follow up some of these targets. And so this is very early results. One of our sources is there's actually two galaxies. The radio source is coming from one galaxy down here with extended CO emission, as well as the carbon line to confirm its redshift. And there's also a companion above it, seen in the ALMA continuum, but not seen in the radio. And again, we clearly detect both lines confirming its redshift of 3.88. So this was exciting. We've confirmed a redshift, but we don't know yet, but it's not as high as we expected. But what does that mean? Well, this is the parameter space in the radioluminosity plane, and the grey shaded region is where we expect our sources to lie. And you can see that this one source, 0917, I talked about earlier, lies right here, and the source on the previous slide lies about here. So we're not quite finding these highest redshift sources, but however, they are still extremely interesting. And that's primarily due to their K-band faintness. So this is an interesting plot that I'll take my time going through. This is the stellar mass radioluminosity plot for various samples of radio-loud AGN. So up here in the top right, these black dots and triangles are masses and limits of most of the known high redshift radio galaxies that we know about. And to help flesh out this parameter space, I've plotted in green all the local galaxies from a large area survey in the southern hemisphere. And these have an average redshift of about 0.1. So this shows you where local galaxies lie. Again, the powerful radio galaxies tend to be have large stellar masses. And then just to make sure what could be the sort of lowest part of this parameter space, we took the radioluminosities of dwarf galaxies detected in the cosmos field, reported a few years ago, and examined where they lay in this parameter space. And you can see that even the most radioluminous of these dwarf galaxies is nowhere near as powerful as some of these high redshift galaxies. And this grey shaded region shows the maximum radioluminosity possible for a galaxy of a particular stellar mass. Now, there's a couple of assumptions gone into this. One, the assumption is that the black hole is accreting at its Eddington rate, and additionally that the galaxy is on the local M sigma relation. So this is technically an upper limit, and so any sources that lie beyond this line the assumptions would be broken. So we have here our radio galaxy redshift 5.5, clearly lying beyond this relation. And then we have one other from our pilot, this green source, and then the other one found from the recent ALMA data right next to it. These radio sources clearly have stellar masses that are far too low for their implied radioluminosity, and this grey shaded region is the loci for the rest of our undetected sources. So where does this put our sources on the black hole mass stellar mass relation? Well, here I've plotted some of our radio detected sources in the larger symbols and compared it to the local relation from RAINS and the voluntary. And then I've also overlaid the position of the JWST sources from Hurricane et al. So instead of finding a needle in this multi-wavelength haystack, are we perhaps finding extreme analogues of JWST's little red dots? So looking to the future, we'd like to follow up more of these sources, and Euclid, which has already been talked about, will be fantastic for this. This will cover much wider areas, but will be comparable to Viking, and then deep fields will be even deeper. So we need high resolution radio observations to help find the positions of the host galaxies of these sources. And then in the color selection for the Euclid optical Y band and the free near-infrared bands, as Matt mentioned, some of these high redshift sources can look very similar to brown dwarfs. However, if you have the presence of radio emission associated with candidates that could be either high redshift galaxies or brown dwarfs, then the radio emission is clearly an indicator that there's an AGN there rather than a brown dwarf. And we've already been looking for candidates to identify in Euclid Deep Field South and the Euclid Deep Field Fornax. We've got around 10 in each. So I'll just put up my conclusions and our notes that radio surveys are powerful tools to find obscured accreting black holes across the universe. And if these sources are not in the early universe, then they're more powerful analogues of the little red dots. So just to emphasize, these black hole limits that we have determined from measuring their jet power are actually lower limits. It assumes really efficient production of their radio jets and really efficient accretion, which is unrealistic. And also assumes Eddington accretion, which of course could be lower, which would push the black hole masses up. So there's a lot more results to come, and particularly from all the future surveys. And I'd like to finish there. Thank you.